Hi everyone. Let's come back to this part 3 of lecture 2. So here what we are going to discuss is how to select the penalty parameter in the ridge regression case. Okay, we are going to talk about ridge, but what we are going to learn here can be useful, very useful for other cases like the lasso and other penalty uh, methods or the regularization methods that we are going to study further in the next few lectures. The agenda for this third part will be we are going to start with how to select the penalty term by using information criteria, and then we are going to discuss how we select the penalty parameter using cross-validation. So the references, if you want to look at information criteria, there is this recent paper that unifies derivation of the archaic. If you are interested in knowing how these information criteria are derived, this is a very good paper. There's also a book on model selection. There's a lot of material about information criteria. And if you're interested in cross-validation, of course, there's our book by Hasty, Tibshran, and Friedman, this nice paper about Jeffrey Racine, and the recent working paper by Chang. Okay. So in general, we have to choose the parameter lambda in the ridge regression, okay, the penalty term, and this will apply to any regularization method that we are going to use. The problem that in general there's no closed form solution. There's not a closed form solution that we can apply and pick the value of lambda. So what we're going to do, we have to base our decision on the data. So we have to use data-driven methods to select the penalty parameter. Okay. So the first thing that we have to do is to decide on a grid. So we have to come up with this grid that we call the capital lambda. We have to select a value of the initial value and then the upper limit, and of course how thin will be this grid. So we have to determine how many terms we will have in the grid, right? We are going to discuss further in the course how to come up with this grid. Okay, and once we have the grid, there are two approaches that we can use to select which is the optimal value of lambda that we are going to select from this set of possibilities. Okay, so we are going to define the set of possibilities. So this set, this grid, capital lambda, and then there are mainly two approaches for us to select the optimal value. One is to use what we call information criterion, and many of these criteria in the literature, the archaic information criterion, the Bayesian information criterion, and Hannan and Quinn, minimum description length. There are many others, but the idea is that we are going to select the optimal value of lambda that I'm calling lambda hat, okay, will be the argument, the value among all the possibilities, the m possibilities that we have, the value that minimize this cost function here. So this is our cost function, okay? It will be the negative of the log likelihood of the data, okay, plus a penalty term. So all these methods, they differ among themselves with respect to the penalty. So in a way, it's a kind of a weird thing because we are selecting the penalty term using another penalized optimization, okay? But in this second penalized optimization, the optimization that I'm defining here, there's no second penalty term involved. Okay, so there's no other term here multiplying this penalty. Okay, and we're going to see the specific definition of this cost function in the next slide. Okay, so this is one possibility. So we have a cost function that's a trade-off between complexity and fit. Okay, so we are weighting here complexity and fit. Okay, and we want the amount of regularization that we are going to use. That's the good trade-off between fit and complexity of the model. The other approach is the so-called cross-validation. And the idea is also very simple. You take your data, take your sample data, for instance. Imagine that this is the set of data points, terribly drawn, okay? And you divide this in two. And you use this first part of the data to estimate your model. And then use the second part of the data here to evaluate your model. So here is basically estimation, and here is evaluation. Okay? And then you're going to estimate several different models here, okay? And then you want to evaluate the models, each one of the models in the second subsample. And you are going to select the best model according to the performance in the second subsample. But then you can always ask, okay, but this depends on how we split the data set. So cross-validation is a way for us to generalize this idea. Okay? And we are going to see also this technique today. Okay, so let's go back to information criteria. Okay, so we want to choose lambda, the penalty parameter, using this trade-off between fit and complexity. Okay, so there are basically three typical choices. As I said, there are many others. These are the typical ones. So basically, what all these methods they have in common is this first part here. This is equivalent to the negative of the log likelihood. And then you may ask, why they are all the same? Why it's just sigma here? Okay? Because we are assuming, implicitly we are assuming that the data is Gaussian. Okay? And if the data is Gaussian, okay, the log likelihood in terms of the fit of the model translates into the log of the variance of the errors. Okay, so this is basically the variance of the errors, of the fitting errors, and it's defined here, okay, down here. So here is where we see the definition of the estimate of sigma square. So it's sigma hat square, and sigma hat square is an estimator of the variance of the errors. Okay. So all these three criteria, they have this part in common. And then you may ask, okay, but if it's not Gaussian, we are using a Gaussian approximation. Okay? And this approximation works fine in most practical applications. Okay? And then you have like two terms here. One, this DF is what we call the degrees of freedom. So it's basically the number of effective parameters that you are estimating in this linear model. Okay? So we have to compute these degrees of freedom. And one thing that's important, as you see here, that I'm making explicit, that the degrees of freedom depends on lambda. So different values of lambda will induce a different degrees of freedom, the number of effective parameters. So the higher the lambda, so the higher is the penalty term in the ridge. What we want, we expect that the lower is the degrees of freedom. Because the higher the lambda, we are shrinking the model towards a model with no covariance, with no parameters, right? Although we are not doing perfect model selection, we cannot shrink exactly to zero, as I have already mentioned that to you, but we can get very close. So we are shrinking the coefficients towards the estimates towards to zero. Okay, so the higher the lambda, the smaller are the degrees of freedom. The lower the lambda, less penalization that we are using, less regularization, the higher is the number of degrees of freedom, right? So this is the measure of complexity of the model. And again, it's common to all the three criteria. So where is the difference between them? On the term that we have here. So the archaic is 2 divided by the number of observations. BIC, or the Bayesian Information Criteria, also known as the Schwartz Information Criterion, is log t over t. So the log of the number of observations that we use to estimate the model divided by t. Or the Hannon and Quinn, that's log of the log of t over t. So these numbers, they don't come out of the blue. There's a whole theory behind them, and depending on the assumptions involved, you get like different numbers. So one thing that's important that you see that for the AIC or archaic, the numerator of this term here is fixed, is equal to 2. It does not matter the number of the observations. Okay, so it doesn't matter the sample size; it's constant here. The other two, the increase with the sample size, but the increase at a slower rate than the denominator. Okay, so as t goes to infinite, as we have the large number of observations, these terms, they go to 0. Okay, so you're not penalizing anything. And so these are, but in finite samples, the amount of penalty will vary according to the BIC and Hannon and Quinn. Although in the AIC, you see the numerator is fixed. So the question is, which one to choose? They have different properties. Okay? So what do you want? You want to select the right amount of regularization. So there's no proof that they, theoretically, that they will give like optimality of the lambda for the reach. You have proofs for this criteria for variable selection in low dimensions with OLS, but in high dimensions, there's no proof of their optimality for regularization, unless you're in very specific cases, but in practice, they work quite well. Okay? But one thing that's important, that in general, the AIC is not consistent. Not consistent for what? If you imagine that you want to select a right set of variables and you want to use AIC to select the right set of variables in finite dimensions, and using OLS, AIC is not consistent. Okay? It usually overestimates the model. The other two here, they are consistent. But this is consistent for the correct set of variables when p is less than t and OLS is used. Okay? For regularization, and especially for the case of ridge, we really don't know. Okay? But empirically, in practice, all these three criteria works fine in terms of getting good forecasting results. Okay. One practical thing is that the AIC tends to select a lower lambda, especially in small samples. It's less parsimonious in small samples. On the contrary, BIC and Hannan and Quinn, they put a higher penalty. Why? Whenever log t is larger than 2 and log t is larger than 2, you expect that these two criteria here to be more rigorous than the AIC, right? But then the question that you may think in practice, okay, but what do we want to do with Ridge? So what means having an optimal lambda, the right amount of lambda? You may think about the risk, the empirical risk, or the out-of-sample empirical risk, okay? So if you are interested in forecasting, for instance, so you want a lambda that gives good forecasts. Okay? So that's our goal in the end of the day. So in practice, you're going to have to play around with these criteria. The good thing is that it's really, really fast, because once you define the grid, if you have m points in the grid, you have to estimate m ridge regressions. You compute the information criteria, the 3 information criteria for each ridge regression, and then you pick the lambda that minimizes your chosen criterion, right? Myself, I prefer BIC. So BIC for me is my chosen guy. Why is that? Because it's consistent in this specific case, but also running Hannan and Quinn is also consistent. But in my practical experience, okay, using different criteria to select the penalty term in different regularization techniques, not only the ridge, okay, but also Lasso and friends, okay, the BIC consistently gives me good results in terms of forecasting when ridge is considered, in terms of model selection when Lasso is considered, okay? So it's a good choice. Okay? Unfortunately, there is no proof of universal optimality for these cases. Okay? So it's more practical guidance here. Okay? So that's what I have to say about information criteria. Again, if you have any doubts, if you want to learn more about this derivation, don't hesitate to ask me. Please come to the office hours or drop me a note, and I'll be extremely happy to discuss more of this with you, okay? So now there's a big question. How can we compute the degrees of freedom? So there is a very nice closed formula for that, for ridge, okay? First, we have to define a smoother matrix S. A smoother matrix is nothing more than a linear operator that you gives y and it gives you y hat, your predictor, right? So and we know, okay, from statistics that the degrees of freedom of a smoother is the trace of the smoother, okay? Of course, this is a matrix operator, okay? So we just compute the trace of this matrix X. In the case of ridge regression, who is S? Is X. X prime X plus lambda I inverse X prime. Why is that? Well, who is Y hat? y hat is beta reach, okay, x times beta reach, okay. So x hat is x. Who is beta reach? X prime x. We have closed formula for that, remember? Plus lambda I minus 1 x prime y. Oh, what we have here, we can define this as our matrix S. So y hat equals S y, and this is our spoofer. Therefore, what is the number of degrees of freedom of reach? It will be the trace. So degrees of freedom of reach associated with a specific value of lambda will be the trace of x prime x plus lambda I minus 1 x prime. Okay? And of course, this already a good expression, is closed formula, very easy to compute in R, Python, MATLAB, C++, Fortran, whatever. Okay? But we can open a little bit more this formula based on what we have learned in the previous block. Okay? So, what's that? Because we know how to decompose this little guy here. And this trace, which is the sum of a diagonal, is nothing more than the sum of dj squared divided by dj squared plus lambda. So here it's pretty clear that the larger is the lambda, the larger will be the denominator. So this ratio here will converge to 0 when lambda diverges to infinity. So the degrees of freedom will be 0, right? And as I mentioned to you a couple of slides ago, it's because you don't have parameters, right? The amount of penalty is so high that you are basically in the limit. When lambda goes to infinity, beta hat goes to 0. No? On the other hand, if lambda goes to 0, what we have is that this will be negligible, so this ratio will be 1, and the degrees of freedom will be exactly what? P. The number of coefficients that we're estimating. That's exactly the number of degrees of freedom of a linear regression in low dimensions estimated by ordinary least squares, OLS. Okay? Bingo. So it makes perfectly sense. Okay? So advantages here, very easy to compute. So it's no computational burden, very fast to estimate the optimal lambda. Once you define the grid, you run a couple of ridge regressions and you pick the right amount of regularization. How will you select the grid? Well, you can start with something very close to 0, so almost no regularization, and you can put a lambda that's large enough to make all the coefficients very, very small, tiny little, okay? And then you have like a number of grid points. How coarse or thin you want your grid, of course, it will depend on your appetite to run regressions, right? Your appetite to run these models in your computer and how large your data set. There are several issues we are going to discuss more, just practical terms on our live meeting and over the course. Okay? So I hope it's all clear. If anything is not clear, drop me a note, come to office hours, bug me during our live meetings. Okay? Now, cross-validation. Okay? So as I mentioned, the whole intuition of cross-validation is to look to a different sample and compare the performance of different models over the second sample, right? So you can look at the mean squared errors over the second sample and compare which model performs the best, okay? So simple way cross-validation 101 is to get one sample will be the training sample. It's the sample where you are going to estimate your model, and then a validation sample, validation or test set, where you're going to evaluate, you're going to validate your models, right? So you estimate the parameters only using the training set. The other observations, you lock them in a safe, right? Don't use it, don't see it, okay? Just take the first set and use it to do all the modeling techniques that you want to do, all your tricks and run all your estimation algorithms, but just looking to the first sample. The second sample is forbidden to you at this stage. After you have estimated your models, with your estimated models, you compute forecasts for the second sample. You compute predictions for the second sample, and then you validate your predictions using the second sample. Okay? So you evaluate your model on the test set. Choose lambda in order to minimize the variance of the prediction error on the test set or any other criterion that you have in mind. Okay? Problem is that the results are strongly dependent on the choice of this training test split. Okay? Solution, let's do multiple splits. So I'm not going to divide like in 2 parts, I'm going to divide in many parts. Okay? So let's define a set calligraphic V that will be a set of indexes of your observations, okay, that we are going to use in the validation set. So these observations, we are not going to use them to estimate the model. Then we are going to define another set of observations, calligraphic T, okay, that will be the observations that we are going to use to estimate the model. So, and only for estimation, okay? The indexes in the calligraphic V set, they are only for validation. We cannot use the same observations, usually in the same indexes in both sets. Okay? So often we want T to be the complement of E. There are some exceptions, okay? But in most cases, we want that. Okay? So then for a choice of calligraphic T and calligraphic V, the 2 sets, we can define the cross-validation loss. Okay? That will be the error over the observations in the validation set. Okay? The squared errors. Where TV here, this quantity here, is the number of observations in the validation set. Okay? So this will be our cross-validation error. Of course, it depends on the amount of regularization that I'm using, and of course in my particular choice of calligraphic V and calligraphic T. Okay? So this is for one split. Now I'm going to define multiple splits. So I have, instead of having one set, I'm going to have capital B sets. So bold calligraphic V that will be this collection of B validation sets, okay? And bold calligraphic T will be a collection of B training sets. And what I can do now, I can average the cross-validation loss over the pairs TB, VB. As you can see, the formula on the screen. Okay? So now, this is not specific to one single split of the data into training and validation set, but it's average over multiple choices, over B choices of this pair training validation. Okay? And this only will depend, the only thing that's now between parentheses here is our regularization term. Okay? So we can have one average cross-validation squared error or cross-validation cost for each value of lambda in our grid. Okay? So the idea, very simple, which lambda should we pick? Well, the one that minimizes the average cross-validation cost. Simple as that. Okay? Intensive, but simple to implement. Right? So, some questions. How should we determine B and the training validation sets? Okay? So what we can do is what we call exhaustive cross-validation, that we are going to select V observations to be in the validation set and consider all possible combinations of training and validation. Okay? So we are going to have the number of validation set will be this binomial TV. Okay? The problem is that's really, really intensive. Of course, you can parallelize that, and with cloud computing, okay, you can do it, but it's not necessary. It's too complicated, and the payoff is not that big. So we can do what we call non-exhaustive CV. And the most common approach is what we called the B-fold cross-validation, where the sample can be partitioned. Sometimes it will be randomly partitioned into B disjoint subsamples with approximately the same number of observations. We'll try to keep this number balanced, of course, but you have to divide your T sample in B disjoint sets. Sometimes one specific sample may have more or less observations than the others, right? So what's the idea? You take your data set. So imagine this abstraction that this gray rectangle that you are looking on your screen is your full data set. Okay? We divide this data set into B parts, our B folds. Okay? Then we take the first fold to be our validation fold, and we use the remaining folds to what? To train the model. So we train here, okay, and we validate here in the blue fold. This will be the first run, okay? And then we compute the mean squared error. This mean squared error will be computed in the blue fold. Label it MSC1. Now, second run, we are going to estimate the model in the first fold, the third, the fourth, so on and so forth. We estimate the model in the gray folds, and we test in the second one, the blue fold. And then we compute the MSE. We do the same thing for the rest. So here we divide into 6 folds, we have 6 runs. Okay? So for each run, we train with the gray sample, we validate in the blue sample, and we compute the mean squared error of the predictions, where the predictions over the observations in the blue sample, in our validation set. Okay? And finally, what we do, we average these mean squared errors over these 6 runs, these 6 folds. And we are going to select the lambda that minimizes this average. So you see, this can be highly intensive because that will depend on the number of folds that you pick. Usually people do like 5-fold cross-validation, 10-fold cross-validation, okay? And it will depend on the sample size, how costly it will be, and how thin it will be your grade. How many lambda points you're going to have in your grid, okay? So this can be intensive. It's becoming less and less expensive due to computational power that we have today, but it's much more computationally expensive than using information criteria. Okay? Problem: this works nice with cross-section data, but the problem is with time series data. And why? Because time series data, this sample here, when we divide it, is not independent on that sample. Because the whole idea of cross-validation is that when you have cross-section, is that the data that you have here is independent of the data that we have here. So we are estimating and testing the model with 2 independent samples. Okay? With time series, we have dependence over the sample. So the gray samples are dependent on the blue samples. How much dependence we expect to have depends on the properties of the time series. If you have highly persistent data, we expect the correlation among the samples to be high. Okay, so this is an issue. Okay, so what has been done? There's this nice paper by Jeff Racine in Journal of Econometrics 2000, where he proposed the HV block cross-validation. Okay, and he has proofs for consistent variable selection in low dimensions. Okay, there's no proof in high dimensions. However, there is this recent paper by Chang who mentioned that one of the assumptions in Racine was not really completely correct, so consistency may be not achieved. Okay, but again, we don't have consistency also in high dimensions for the information criterion. Okay, so we are basically on the same page here. Okay? But so far what we have as best solution for cross-validation in time series is this proposal by Jeff Racine that I'm going to show you now. So the idea is that we are going to create a void between two sets of observations, 2 samples. Okay? So we are going to do is the following. We take one specific observations and we are going to remove V observations around that sample. So the idea is, if we go back here, is that we want to create around the splits some kind of void, some kind of open space, a vacuum. Okay, so we are going to remove these observations. It's going to become clear here. Okay, so the validation set will have 2V plus 1 observations. Okay, so maybe the idea is to be clear if we look at this diagram. Okay, so take the ith observation. Okay, so we want to include this observation in the validation set, right? So we are going to create a block for the validation set. So we're going to take V observations to the left, V observations to the right. Okay? So we have 2V plus 1 observations. So this will be our validation set. Okay? And now we are going to, the B-fold cross-validation, what we usually do, we take all the other observations as training set. But here we're not going to do that. We are going to include our void, our vacuum. So we are going to take H observations to the left of our validation set and H observations to the right of our validation set. And we are not going to use those observations. They are going to throw them in the bin. Forget about that. And then the rest will be our training set. So that's how we define the blocks. So if we go back, here is what we are doing. So this is the validation set. Okay, let's remove something here. Let's remove something here. Take it out. Let me draw this in a better way. So it's like here. Take it out here. Take it out here. So this part here we are going to throw in the bin. We are going to estimate the models here. And we are going to validate here. Okay? And we are going to do this over the sample. This is the H-knee block cross-validation. So if you have time series data and you want to use cross-validation, use HV cross-validation. Okay? If you ask my opinion, I would say don't use cross-validation. Use information criteria. Faster and always good results. Okay? Cross-validation, really unstable. You lose observations. You need usually a large set of observations in very small sample. You have problems. So usually I prefer to use BIC. This is a universal rule. You know, maybe there will be problems where cross-validation will be better. But my first choice is always to try one information criterion to select the optimal parameter, optimal penalty term. Okay? All right, so there are some motivating questions for you here, for you to think about. Try to think out of the box about what you have learned during these 3 blocks. And I see you all on Friday, and we can have a nice discussion about this material. Okay, so thank you very much. Have a wonderful week. See you on Friday.